At this scale, the Sun is 1 metre wide. Imagine a 1 metre wide beach ball. Where are the planets and how big are they? On this walk, we will cover approximately 50 astronomical units, about 5/10,000ths of a light year. We begin at about 50 metres. At this point, we encounter Mercury, which at this scale is 3.5 millimetres wide, size of a grain of rice. Mercury is very small. The largest moons in our solar system are larger than Mercury is. Like our own moon, Mercury is covered in craters. It hasn't been geologically active for at least 3 billion years. It is the closest planet to the Sun, obviously, and it's locked into a 3-2 spin-orbit resonance, so it spins 3 times for every 2 orbits that it does. Mercury year is 1 Mercury day and a half. Moving on up to 80 metres, we get to Venus. At this scale, about 9 millimetres wide, about the same size as Earth, the size of a pea. Indeed, probably earlier in the life of the solar system, Venus looked a lot like Earth. We don't know for sure, but that's the accepted theory. It probably had surface oceans, a climate very similar to ours. But nowadays, Venus's atmosphere is almost entirely carbon dioxide. In other words, runaway greenhouse. At 110 metres, Earth. Again, about 9 millimetres wide, about the size of a pea. At about 180 metres we get to Mars, and it's about 5 millimetres across, a bit less, about half the width of Earth or Venus. We like Mars a lot despite the fact that it's further away than Venus, because it's much more hospitable. Venus is the hottest planet in the solar system, much hotter than Mercury. Reason very simply being that it's full of carbon dioxide. Unlike Mercury, it doesn't have a cold side. Mercury's day side is hundreds of degrees centigrade. Its night side is negative hundreds of degrees centigrade. Venus is several hundreds of degrees centigrade all over, all the time. Like Venus and Earth, Mars sits in the habitable zone, which means that it probably has liquid water somewhere on its surface. We haven't found it yet, but all the evidence suggests that it is there. At 320 metres, we encounter Ceres, a dwarf planet. At this scale, about 0.7 millimetres across. Ceres is tiny. Many of the moons in our solar system are larger. The funny thing about Ceres is we know it's here because we looked for it. In the 18th century, a German astronomer named Johann Titius noticed that the planets, for some reason, seem to conform to a remarkably simple formula with regard to their orbital distances. Ceres was the missing planet. We looked at that particular orbit and we found not only Ceres, but all of the rest of the asteroid belt, which also orbits at this distance. Ceres, in other words, is just the largest of the asteroid belt objects. It is the only one that is in hydrostatic equilibrium, in other words, it's a sphere, and therefore the only dwarf planet that we find in our solar system inside of the orbit of Neptune. It's really interesting because the Titius-Bode law, it's called the Titius-Bode law because it was popularised by Johann Bode around about the same time, late 18th century. Has no theoretical basis. It was never offered with any theoretical basis, it's just an empirical observation. Many since then have tried and failed to find a theoretical basis for it. And yet, it has remarkable predictive power. Not only did it predict the orbit of Ceres, it also predicted the position of Uranus and Pluto, another dwarf planet. And yet, we have no idea why. Here's the kicker. Looking at other solar systems outside our own, looking for exoplanets, the evidence seems to suggest that a power law relation seems to hold, of fundamentally the same form as the Titius-Bode law, in most solar systems, not all, but most. And indeed, simulations of planetary formation corroborate this. Unfortunately, like I said, it holds most of the time, not all of the time. Neptune, for example, does not conform to the Titius-Bode law. It's one of those things. It's really accurate, except when it's not. Doesn't stop us from using it, however. In the search for exoplanets, a number of surveys have used a power law relation to predict the placement of other planets in systems in which we've already found, say, at least one planet. And this has actually worked a number of times. But again, no one knows why. It's a mystery. Maybe one day we will know. Cruise on up the road here. When we get to these traffic lights, we get to Jupiter. It's 10 centimeters across, as opposed to Earth's 1 centimeter. It's huge. It is very large. It is 10 times the width of Earth, and it's 1/10 the width of the Sun. It inclines one to wonder, what is the upper limit of the size of a planet? A related question, of course, is what's the difference between a planet and a star? Is it one of composition? Well, no. Jupiter is a gas giant. It's made of hydrogen and helium almost entirely, just like the Sun is. They are fundamentally the same kind of thing. Is it a difference of size? Well, no. The smallest stars are smaller than Jupiter is. Jupiter is the most massive planet in the solar system, and as it turns out, Jupiter is about as large as planets get. At this scale, the primary determinant of size is temperature, not mass, because of course we're talking about something that is mostly gas. If you added mass to Jupiter, if say an enormous cloud of hydrogen and helium wafted through our solar system and was somehow mostly absorbed by Jupiter rather than our Sun, what would happen? At about 1.3 times the mass of Jupiter, it would start shrinking. In other words, as you added more mass, it would get smaller rather than larger. At about 13 times the mass of Jupiter, it would get to the point where you had enough mass, enough gravitational force to fuse deuterium. Deuterium is an ion of hydrogen. It is not abundant in the universe, and so fusion of deuterium is not enough to turn something into a star. At this point, Jupiter would become what's called a brown dwarf. Brown dwarfs are not quite planets and not quite stars. They behave a bit like both. We've seen plenty of them. First predicted in the 1960s, we observed the first brown dwarf in 1995, and since have found many more. However, brown dwarfs seem to form around stars with low metallicity. Our own star has lots of metals in it. And indeed, that's the reason why our planets have cores, whereas brown dwarfs tend not to. The evidence seems to suggest that Jupiter couldn't turn into a brown dwarf because it has a core, and yet there's no theoretical reason at all why that couldn't happen. Bit of a mystery, no one knows why. Maybe one day we'll know. At about 80 times Jupiter's mass, you would have enough gravitational force to fuse hydrogen. Hydrogen fusion is the engine of the stars, and as such, at that mass, you would have a star. If you continue to add mass to it, it would grow larger very rapidly, larger and hotter, and it would turn more blue in colour. But more about that on another walk. If you're curious about why the planets would get smaller if you added mass to them, the short answer is due to the effects of gravity. They're collapsing in on themselves. The slightly longer answer is it's due to a phenomenon called degeneracy, a quantum effect, basically scaled up to the macro. I won't pretend to understand what degeneracy is, but you can look it up if you're interested. Let's cruise on up to the Blue House roundabout. This is kind of where the town more ends. At this point, about 1 kilometre away from where we started, we encounter Saturn. At this scale, about 8 centimetres across, the size of a cricket ball. Jupiter is significantly more massive than Saturn it is, but it's not much larger. Saturn's interesting because it has rings, of course, but I think it's interesting for another reason. If you look at a photo of Saturn, you'll notice that it's squashed. It looks like someone has sat on it. The reason's very straightforward. Like I said before, hydrostatic equilibrium basically means that something is a sphere. But in fact, everything in hydrostatic equilibrium will be slightly wider at the equator than it is at the poles, because it's spinning. Saturn happens to be spinning very quickly and is therefore about 10% wider at the equator than it is at the poles. I think this is really interesting because hydrostatic equilibrium implies different shapes altogether if you get much faster than the rotational speed of Saturn. But we'll come back to that on another walk. Cruising on up to the retail district, we'll pass some very expensive houses. This is a very nice part of town. And then we'll get to the high street, which is cafes, bars, shops, lots of different kinds of things. And of course the Sainsbury's, where lots of us go for our groceries. At this point we encounter Uranus. Uranus is 4 centimeters across at this scale, half the width of the gas giants. Now Uranus is what's called an ice giant. What you need to understand is that astronomers use common words to mean different things to what we commonly mean them to mean. Ice doesn't mean that Uranus is solid, and indeed it's not. Rather, all 4 planets, the ice giants and the gas giants, are in what's called a supercritical fluid state. Supercritical fluid is the phase of matter between liquid and gas, where the distinction between them breaks down. It's not quite a liquid and it's not quite a gas. It behaves like both. The difference between the ice giants and the gas giants is basically one of composition. Astronomers, when they say the word gas, mean hydrogen and helium. When they say the word ice, they mean volatile chemicals with a freezing point above 100 Kelvin. So water, ammonia, methane. Uranus and Neptune are mostly water, but they have enough methane in them to turn them blue. Speaking of Neptune, let's continue up the road. You eventually get out of the high street into the kind of commercial sector, lots of doctors, lots of lawyers, things of that nature. Big sort of tech center, transport hub, very large school, and then these traffic lights here, where we get to Neptune. Now, Neptune is kind of a border of the solar system. Inside of the orbit of Neptune, everything orbits on the ecliptic plane, basically a disk around the sun. That includes all of the asteroid belt objects and all of the planets. Outside of the orbit of Neptune, orbits get oblique to the ecliptic, so more like a sphere than a disk. This is why we refer to some things as trans-Neptunian. This is also roughly where the scattered disk starts, and also the Kuiper belt. The Kuiper belt is trans-Neptunian objects which are in a stable orbit. The scattered disk is trans-Neptunian orbits which are unstable. We'll talk a bit more about that on another walk. Cruise on up the road here. We are now very much in a residential zone. It's quite a nice zone. It's nice houses, pretty posh, lots of trees. But otherwise, very much the outskirts of Newcastle upon Tyne. Still a busy road, the Great North Road, but cars on this part of the road are largely leaving or coming into Newcastle. It's at about this point that the footpath ends, and the road splits off to go into the countryside. We're about 4.9 kilometres away, and we are at the aphelion of Quaoar. Quaoar is a dwarf planet just like Pluto or Ceres at this scale, 0.8 millimeters wide, grain of sand. I said I wasn't going to walk further than 5 kilometers because 5 kilometers is a human distance, but Pluto is only about 300 meters that way. And at this scale, 1.7 millimeters wide, much larger than the other dwarf planets, except for Eris, which is about the same size and significantly more massive. I won't talk about Eris now because obviously it's much further away. We'll talk about it next time. But I will just point out, this, in effect, is the reason why we didn't have a good photo of Pluto until very recently. We were trying to take a photo of a grain of sand 5.3 kilometers away. This is also the reason why we don't have photos of Quaoar, Haumea or Makemake. But I won't talk about them now. I'll talk about them next time.